Good day, everyone. Yeah, we are here again, and in this video, we'll be formalizing one of my theorems. Yeah, and that's how well, and this covers the sort of the general case of the perfect cuboid problem. Which, yeah, once we're talking about an open problem here, and there's ways that need to approach that sort of a claim with a caution. And so my goal would be to formalize that with assistance of AI, still with GitHub Copilot, and try to see what we can do with that. And then just before we can lay any claims on having a foolproof, yeah, I would reach out to a professor who works around this problem just to get insights to see whether this indeed is a foolproof. Yeah, and so this video the focus would be to formalize the theorem 2.13, which is covering the general case for composite cases, for a given side, which in, was considering what we call maybe side A, but generally once it's the symmetry. Once it applies for one case within this context, uh, you can can determine you can infer that it applies to other like cases. So we'll get started, and so we'll share screen, and so we go here. Yeah. In fact, it's even convenient to deal with VS Code, but it's here. Yeah, yeah. These are some of so if you have seen some of my previous videos so far, you must have some sort of idea of where what all of these correspondences come from, And so yeah, this is it. Yeah, this is an updated version of my paper before, an updated version. And so we scroll, yeah. And when we go to my Figshare, I'll put this same paper on Figshare, which is basically this website here. Mm, this. So this was just a paper I put out, just yesterday. And so this is basically about I'll update this paper. There have been some few updates, which is now in this one. And so we'll go to the main text, scroll down, down, down. So basically, this theorem 2.13, this, yeah, we'll go back. So, so this is, so I just copy pasted this into here. This is theorem formalize completely in lean language. Formalize completely in lean language. So yeah, let's see how this will do with that. Let's see. All of these stories. Jeez. Let me know. Let me see. What did it say? It says certainly here is a complete formalization in 4 of your theorem in producing MATLAB 4 conventions. This formalization is at the level of a mathematical statement and proof sketch, not a proof computer verified proof, since the full proof would require a lot of auxiliary lemmas about device errors, prime factorizations, and the structure of the perfect cuboid equations. However, it's written in a way that is suitable for lean and can be expanded into a full. So let's see. Let's look at this MATLAB list. Let's go through. You can go to the website and see. Okay, so let's see. MATLAB data nat.prime. So yeah, MATLAB, then you come down to data, and then you see data. Let's see, so MATLAB data, then nat, then prime. So we have we're on MATLAB data nat prime, and prime is here. So good. So MATLAB data nat and factorization. Let's see what the factorization is here. Okay, factorization is here. So yeah, and then data, then fin type, then basic. Let me see. Data, data and fin type, data, fin type, and basic. So yeah, I think yeah, yeah. Okay. This is what it says. So it says that a structure perfect cuboid and encode the definition. The theorem no perfect cuboid with composite side states that the non-existence of composites depicted on the proof is sketched with comments indicating where the proof analysis and exponent argument would go. The full proof would require encoding the device structure, the cuboid equations, and linear substantial. Okay. So let's see. Let's ask it to give a more detailed encoding. We'll see how far this can go in helping us formalize this proof to the best of our limited ability. And then if it works, it can translate it into LaTeX language and see. Yes, so it's asking whether it wants it all expanded to include the full algebraic expressions. And I'm like, yes. We want all the heat, all the smoke. It should be all full. We see what happens. Okay, let's see why admit. Yeah. Admit is used as a placeholder when a final algebraic contradiction is formalizing. To complete this proof, you must encode, prove the exponent mismatch for all possible cases. Which is a technical but feasible task in Lean. Sure. Yeah, it says to fully complete the proof, you will need to expand the arithmetic and EXP balance, which some appears somewhere. I think over here. in the exponent imbalance. It should be about that. To show that the exponents for prime subscript j cannot be matched under strict ordering. It's a technical but routine step in Lee. Let me know if you want the explicit arithmetic for the exponent comparison. Yeah, let's go for that. This is what it does. So it encodes the divisor structure and algebraic expressions for both sides of the cuboid equation. It defines the exponent for each prime. Proves under strict ordering, the exponents cannot match, so the equation cannot hold. This matches the contradiction in the main text and provides universalness. So we'll copy paste this. We'll copy this into DeepSeek. Translate into LaTeX language. So let's see. Okay. This is how it is. Okay. So with AI assistance, you have been able to formalize Theorem 2.13, which is this. So which essentially means that we are done with the formalizing the lemmas and theorems in this paper. The rest are definitions, yeah. So that's what we have been able to do today. So I think we've been able to formalize the proofs for each of the for lemmas and theorems here and there. So in the next video, the goal would be to I'd be live gathering all of these lemmas or theorems formalized by the assistance of GitHub Copilot. We gather them into one GitHub, where you can all find all of these codes, and yeah, it's all part of a long-term goal. So once that is done, then yeah, we'll see what is next. So this is where we end the video for now, and thanks for your time and thanks for watching. Yeah, so see you next time. Ciao.